Hello everyone, Assalamualaikum warahmatullahi wabarakatuh. So through this video, I'd like to deliver my presentation for the tutorial session of ICO ICT 2020 with the title, What Can an LP Do in a Disaster? My name is Yunita Sari, currently serve as a lecturer in the Department of Computer Science and Electronics, Universitas Gadjah Mada, Yogyakarta. So this topic is actually pretty interesting for me because my area of expertise is more on the NLP, while this year ICO ICT topic is more on the disaster management or mitigation. So through this tutorial, I try to explore how NLP can be applied for disaster management or disaster mitigation purpose. Alright, so we start with this image in which showing how in the disaster time communication is vital. So there are 4 parts here that needs an intense communication during the disaster time. There are government, first responder, general public, and also volunteers. So the government and first responder need to communicate and having coordination of resources, services, and also action plans. And responder to general public, probably offering services and also safety guidance. General public to responders, probably seeking medical, food, shelter aid, and safety concern. Government to general public, probably conveying a message about disaster services, emergency shelters, resource allocation, and also infrastructure maintenance. Volunteers to the government, offering aid, money, and human resources. And last but not least, among the general public itself, just to make sure that they are safe during the disaster time. All right. But in most of the time, if the scale of the disaster is big, there are a lot of damage in the infrastructure, including the communication infrastructure. So communication through phone is probably not available during that time. So here is probably we can explore social media as a way to communicate during this difficult time. Alright, so there's actually a study, an international study conducted by a researcher at the University of Madrid, National Information Communication Technology Australia, and also the University of California in San Diego, in which they have found that social network activity during and in the hours following a natural disaster actually can quickly reveal the extent of damage that took place in a particular area and time period. So this is very interesting because usually collecting information regarding the damage or any other thing during the disaster time is very challenging. Another study is also conducted by the University of San Francisco MPA program that created an infographics that explains how social media is creating a major changes in the disaster recovery and response. So the highlight here is the communication is actually the key to disaster management, and then we try to explore social media as the way to communicate. So this is one of the part of the infographics from the University of San Francisco MPA program, showing how the social media take a role in the tornado season in the US. So 2011 was marked as the deadliest tornado year in the US ever because there were more than 1,000 tornadoes at that time. So at that time, a Facebook page were dedicated to tornado recovery in Joplin, and there were more than 100,000 members within days of devastating tornado. And this page is used for mobilizing volunteers and also assisting in the search for survivors. So also there's a case in Tuscaloosa in which there is a social media website called Tuscaloosa Forward that were created that let residents share ideas for rebuilding after the disaster happened. So surprisingly, there were 300 ideas shared by over 4,000 visitors. And also there's a case, a school system in Tuscaloosa posted a request for volunteer to help with school cleanup effort on social network. And then surprisingly, just within 30 minutes, 80 volunteers arrive. Okay, so this is pretty amazing. Another case is from the Japan tsunami. So there were more than 1,000 number of tsunami-related tweets sent each minute during the tsunami and resulting nuclear fallout. And there is a case here. There's one hospital in Japan located just 27 miles from the Fukushima nuclear plant, in which they desperately needed to move 80 patients away from the danger. And then probably because of the communication infrastructure is not available during that time, a hospital staff took Twitter messaging U.S. Ambassador John Roos, who was able to alert the embassy and coordinate with Japan's ground self-defense forces, who evacuated the patient. And from this disaster, also Facebook recorded there were 4.5 million status updates from around the world containing the words Japan, tsunami, and earthquake. That 80%, 84% of total status updates. So, well, it is showing that social media is actually can be used as a communication tools during the disaster time. So, there is a research work by Sakaki et al. In 2013 that saying tweet as a sensory value. So they're making analogy of a tweet as a sensor. So actually, the how the tweet works and how the sensor works is pretty similar in this case, but of course the input will be different. So for Twitter, the input will be target events, and the observation was done by the Twitter user, and in some point it will create a probabilistic model, and this actually pretty similar with how the real sensor works. And in the left part, there's an image from the Sakaki et al. Works in which it depicting how the estimation. So Sakaki et al. Trying to estimate the earthquake center based on the tweet with the several keywords. And actually, it's pretty close with the actual earthquake center. Okay, another work from the early et al. In 2012, and Robinson et al. In 2013, making tweet as a social sensor. So at that time, they use tweet as earthquake detector. So this is example of the first-hand report and not first-hand report. So first-hand report is actually some kind of tweet post that created by the user in the time of the disaster when it just happened. So it's kind of like, wow, earthquake, that was a good one, and so on. Compared to the not first-hand report, it's more on the like a post that probably just created after an hours or probably more longer after the disaster time. So from this tweet post, actually they are trying to differentiate or classify between the positive, the first-hand report and not first-hand report. And also from this tweet, they they suggest some kind of future work for intensity prediction based on impact description. So usually when people tweeting about disaster, they're not just tweeting about disaster itself, but also the impact of disaster probably towards the infrastructure. So for example here, the example of the tweet post, it can be classified as 6 strong in the MMI scale. Alright, the other work from Aramaki et al. In 2011 about influenza epidemic detection is probably quite related with current COVID-19 pandemic situation. So they're trying to create a model that could classify tweets into 2 different classes, the positive influenza and negative influenza. So the positive one is probably more on the showing the symptoms like a bad influenza is going around in our lab, so it's probably more on the positive sign, while something like headache, you might have flu, is more on the suspicion, is probably not a positive sign. Also, other study by Takahashi et al. In 2011 trying to generate a hay fever map, which is shown in the right part of the presentation, and it is actually pretty useful for people that have pollen allergic. Yeah. Okay, so that's the example of some research work. Okay, so there is one more here. Oh, okay, this from Neubik and Matsubayashi from 2010, in which it's actually I took their title as part of the title of this tutorial. They conducted research about safety information mining. So there are 2 different steps in their study. First, they're trying to do the name entity recognition and also safety information classification. So safety information classification is basically they're trying to classify the tweets into 9 different labels with its own definition, and then from that they also extract or recognize the name entity, including people and location, so that they know what happened with the people in which location. For example, in this example, it can be classified into the missing, and then the people that involved are Tanaka Taro and Hanako, and the location is in the Kasanuma city. All right. So from that research work, it's actually I can conclude that there are 5 main steps that usually conduct during for the research. First is data collection. This just pretty straightforward, collecting or scraping data from the internet. It can be from social media, any social media. And also the second step is data filtering. It is pretty important because not every tweet or post with disaster keyword is related to disaster. And also annotation. This is step manual annotation to create training data, usually utilizing crowdsourcing annotation tool or employing volunteers. And the annotation result or the training data can be used for training the machine learning model, mostly supervised learning model. And the model can be used for predicting the new data. All right. So from annotation that already conducted, usually it will be resulted in a corpus development, and there were some corpus that actually shared for public for free. One of them is Crisis NLP. This is probably one of the most comprehensive one. It resources for research on crisis informatic topics, and if I'm not mistaken, it consists of, if I'm not mistaken, 14 different data set related to crisis or disaster. There is also crisislex.org. This is a repository of crisis-related social media data and tools. Other resources that I can list here from the COVID-19 NLP resources, and also some other corpus that were produced after the research fog. All right, but the challenge here is actually, you can see here that most of the work that have been conducted is usually using the supervised learning, and we already knew that supervised learning needs a lot of training data. So there is a problem here in creating training data. First, annotation may need a lot of effort, especially in the disaster time. Annotation by volunteers probably one of the alternative, or if there is no volunteer available, the annotation can be done using specific crowdsourcing platform, in which it should be expensive to use that. And then also in some cases, labeling may need expert, for example, for the medical data set, and also annotation is time consuming and boring. But the fact here, actually the number of unlabeled data is far more bigger than labeled data. So the question here is, can we make use of them? Okay, so the next discussion is more on the how we could leveraging the unlabeled data. So we know that in general, the machine learning method can be divided into 3 different techniques: the supervised learning, semi-supervised learning, and unsupervised learning. And in this case, supervised learning using all labeled data in the training time and producing a supervised model, while in the semi-supervised learning, using some labeled data and a lot of unlabeled data, while unsupervised learning doesn't need labeled data at all. So the difference between this method is actually in the how many labeled data used in the training times. For this tutorial, I'd like to focus more on the semi-supervised learning, on how we could leveraging the unlabeled data. All right. So this is pretty interesting because I found this graphic showing how semi-supervised learning research paper is increasing. Yeah, the number is increasing year by year. Semi-supervised learning is probably not as popular as supervised learning, but actually the number of research in this area is increasing by year. All right. Okay. So the question here is, do we learn from both labeled and unlabeled data? So actually learning actually exists long before machine learning, right? And where or not we human actually perform semi-supervised learning. So if we take a look in the cognitive science, in which that's how the computational model of how human learn from labeled and unlabeled data. So let's say there's a concept learning in children. X is animal and Y is a concept, for example, cat. And then children learn their surrounding, for example, from their surrounding, for example, from the parents that point out that furry white animal is cat. And then in some point, children also observe animal by themselves. So when the children see other variation of cat, they could actually observing that this is the same as the furry white animal that point out by their parents. All right. So how actually unlabeled data can be helpful here? So the concept is we actually can use accessible data to improve decision boundaries and better classify unlabeled data. So this image, these 4 graphs in the right of this presentation showing this one is the labeled data and this one the label and unlabeled data. This one, using the supervised learning, is actually can create some kind of decision boundary that differentiate the area of the rectangle and circle. But here, if we add the unlabeled data, or in which we are using the semi-supervised learning, it can shift the decision boundary. So hopefully, using the unlabeled data, we can have a more accurate prediction when it is tested in the test data. Okay, so in this tutorial, we will be discussing 3 different algorithms: self-training, pseudo-labeling, and also multi-view training. So this is this algorithm is actually not new algorithm, but I'd like to give some kind of foundation so that we could be more prepared when we exploring more advanced algorithm, semi-supervised algorithm. Okay, so this is the notation that will be used in this tutorial. So there's an instance X, label Y, and there's a base learner F, and we have label data XLYL, and then unlabeled data XU, in which it available during training. And usually the unlabeled data, the number of unlabeled data is far more bigger than L. And we have N here, which is the addition of L and U, the label and unlabeled data. And also we have the test data that not available during training. All right, so this is the self-training. So self-training algorithm, it was first proposed by Yaroski in 1995 as an approach towards sense disambiguation in text document. It was used to predict the meaning of words based on their context. So this is the algorithm of the self-training. So initially, for example, we have L as the labeled data and U the unlabeled data. So what happened is we train F, the base learner, from L using supervised learning. So any kind of supervised learning algorithm. So the next step, then apply F, the model, to the unlabeled instance in U. And then the next step, remove a subset S from U, and then add the XFX, given the X member of S to L. So it's like we are trying to predict the level of unlabeled data and adding probably some of the data from the unlabeled data to the training data, and then repeating the process again until the stopping criterion is found. Alright, so in the self-training, there's an assumption that ones on high confidence prediction are correct. Okay, because, well, of course, there is no label in the unlabeled data. So the assumption here, one on high confidence prediction are correct. So there are some variation of self-training here. We can add a few most confident XFX to label data. or add all the XFX, the prediction from the unlabeled data to labeled data, or add all the prediction XFX to labeled data, but weight each by confidence. Confidence here probably in the supervised learning is kind of like the probability resulted from the machine learning model. Okay, so self-training is actually a wrapper method, and the choice of F here is left completely open. So any kind of machine learning model can be used, and it's good for many real-world tasks like NLP. But there's a limitation of the self-training because the mistake by F can reinforce itself, meaning that if the base learner, the quality of the performance of base learner is not really good, it will result on the wrong prediction in the next iteration. So it is important to make sure that the quality of the training data, the label data in the first place, is good in terms of the distribution of the data or the data balance. All right. Okay, and then self-training is actually can be applied to deep neural network, and this work called pseudo-labeling, it was done by Lee in 2013. Okay, so I will recap a bit about the multi-layer neural networks. Let's say we have multi-layer neural network with m layers of hidden units. So we have sk here as a nonlinear activation function of the kth layer, for example, a sigmoid function. And then we have fi here, which is the which are the output unit used for predicting target class, and also xj, which is the input values. So we have the input and output values and some and m layers of hidden units, right? And then we have sigmoid activation function here, and also the network can be trained for the purpose of minimizing supervised loss function. So this is the loss function, where C is the number of labels, and then yi is the one of k code of the label. Okay, fi is the network output for the ith label, and x is the input factor. And let's say we are using the sigmoid output unit, we can choose cross entropy as a loss function here. All right. Okay, so I will not describing about how the training works. Probably it can be using the stochastic gradient descent in this case. So the pseudo labels actually target classes for unlabeled data as if they were true labels. So in his work, Lee picked up the class which has maximum predicted probability for each unlabeled sample. Remember that unlabeled sample doesn't have any label, right? So here yi prime equal to 1 if I is argmax, the maximum value of the maximum predicted probability, and 0 otherwise, right? And then the pretrained network is trained in a supervised fashion, the network is trained in a supervised fashion with labeled and unlabeled data simultaneously. And then the overall loss function here is actually combination between the loss function of the labeled data and loss function in the unlabeled data. So here the left part is the loss function for labeled data, and the right part is loss function for unlabeled data. And there's an alpha t here. It's actually a coefficient balancing loss of labeled and unlabeled data. So there are something that we have to remember here, that the total number of labeled and unlabeled data is quite different. Means that, okay, unlabeled data, the number of unlabeled data usually bigger than labeled data, and the training balance between them is quite important for the network performance. That's why the coefficient, the choice of coefficient here need to be done very carefully. All right, because it cannot be too small or too large. So the alpha t here is slowly increased, and then it is expected to help the optimization process to avoid poor local minima, so that it is expected that pseudo label of unlabeled data are similar to true label as much as possible. So in his work, Lee set this value of alpha t based on the epoch. So t is time here is the iteration or the epoch, and t1 and t2 is a certain point in the epoch. So he set different value for t1 and t2 without pre-training and with pre-training, because he was also used the denoising autoencoder in his work. All right. The other that's for self-training, and then the other semi-supervised learning is multi-view code training. It's from Blum and Mitchell from 1998. So it is actually still an extension of self-training, but it used multiple supervised classifier. So in code training, it used 2 or more supervised classifier, and then it will iteratively train on the labeled data and adding their most confident prediction to the labeled data set of the other supervised classifier in each iteration. But here there's a note that in order for code training to succeed, it is important that the base learner are not too strongly correlated in their prediction. So here, each instance is represented by 2 set of features. X consists of x1 and x2. X1 is the first feature and x2 is the second feature. And then this is actually a natural feature split or multiple views. And the code training idea is train F1 classifier and F2 classifier, and the 2 classifier teach each other. So in the work Plum and Mitchell at that time, they were trying to classify university website, if I'm not mistaken, using 2 different features. Okay. So there are some assumptions in the code training, multi-view code training. First is future split x1 and x2 is axis. But it's actually when using the x1 or x2 alone is already sufficient to train a good classifier. And x1 and x2 also conditionally independent given the class. And this is the code training algorithm. We start with training to classifier F1 with the labeled data 1 and F2 with labeled data 2, and then classify XU with F1 and F2 separately, right? So at F1K most confident X F1 X to F2 labeled data, so to other classifier, to other training data, and then vice versa, and this process will be repeated until stopping criterion is met. Alright, that's the code training. So there are some pros and cons regarding this algorithm. So the pros is code training is very simple wrapper method, same as the self-training, and it can be applied to almost all existing classifier. And then compared to the self-training, it is less sensitive to mistakes. But the cons, natural feature split might not exist. It's probably not exist for data, not for every data set. And then in some point, well, model using both features should do better, right? Okay. And there is actually a work by Triguero et al. 2015, which tried to compare between an array of semi-supervised learning, and it was applied in an array of dataset as well. So this is, I just pick one of the result here, comparing the semi-supervised learning with the supervised learning. So here, this is the difference in average test result between outstanding models and C 4.5 and SMO. This two is the supervised learning. And for this case, for this test result, the supervised learning obtained around 79 to probably around 80% on the accuracy using the full training data set. While in the same time using different type of semi-supervised learning, in which in this case self-training, co-training, and democratic co-training and co-bagging, there's actually pretty close. It's not that different. I mean, like just using 10% of the label data, one of the semi-supervised method can obtain around 73% of the accuracy. And when the number of training data is increased up to 40%, the performance also almost similar as the in this case it's the SMO or the one of the supervised learning. So we can see here that actually in the time of that the label data is not available, there are not many label data is available, we can use semi-supervised learning, and the performance is quite close to the supervised learning, and then of course it will somehow the advantages of using the semi-supervised learning of we don't need to do the annotation, right? Okay. All right, and then to close this tutorial, actually I would bring this cake, the picture of this cake, and then mentioning the Jan LeCun's cake analogy. I'm sorry for the wrong pronunciation. So Jan LeCun is one of the probably deep learning frontiers. He said in one of the conference, if I'm not mistaken, NIPS in 2016, that most of human and animal learning is unsupervised learning. And then if intelligence is a cake, the bulk of the cake is unsupervised learning, the icing on the cake is supervised learning, and the cherry on the cake is reinforcement learning. So even though in this analogy the semi-supervised learning is not mentioned, but I want to highlight that in this case, in most of the time we are more focused on the supervised learning, but it is actually just the icing on the cake, because when we are looking at the real case, the label dataset is scarce, and then while in the same time the number of unlabeled data is available. So in this case, there is area that we should explore here regarding the how we could leverage the unlabeled data. Alright, so hopefully this tutorial can provide some kind of research guidance, so we could actually trying to implement NLP for the disaster management or mitigation purpose. In the same time, we also exploring more on the unlabeled data. Okay. All right. Thank you very much, and that's all. If you have any question, please don't hesitate to ask in the Q&A section. Thank you.